Chapter 1 Review. Challenge Problems. 88. The first atomic bomb was detonated on July 16, 1945, at the Trinity test site about 200 miles south of Los Alamos. In 1947, the U.S. government declassified a film reel of the explosion. From this film reel, British physicist Graham I. Taylor was able to determine the rate at which the radius of the fireball from the blast grew. Using dimensional analysis, he was then able to deduce the amount of energy released in the explosion, which was a closely guarded secret at the time. Because of this, Taylor did not publish his results until 1950. This problem challenges you to recreate this famous calculation. A. Using keen physical insight developed from years of experience, Taylor decided the radius r of the fireball should depend only on time since the explosion, t, the density of the air, rho, and the energy of the initial explosion, E. Thus, he made the educated guess that r equals k, e to the power of a, rho to the power of b, t to the power of c, for some dimensionless constant k and some unknown exponents a, b, and c. Given that open bracket, e, closed bracket, equals m, l squared, t to the power of -2, determine the values of the exponents necessary to make this equation dimensionally consistent. Hint. Notice the equation implies that k equals r e to the power of -a, rho to the power of -b, t to the power of -c, and that open bracket, k, closed bracket, equals 1. B. By analyzing data from high-energy conventional explosives, Taylor found the formula he derived seemed to be valid as long as the constant k had the value 1.03. From the film reel, he was able to determine many values of r and the corresponding values of t. For example, he found that after 25.0 milliseconds, the fireball had a radius of 130.0 meter. Use these values, along with an average air density of 1.25 kg per meter cubed, to calculate the initial energy release of the Trinity detonation in joules J. Hint. To get energy in joules, you need to make sure all the numbers you substitute in are expressed in terms of SI base units. C. The energy released in large explosions is often cited in units of tons of TNT, abbreviated TTNT, where 1 TTNT is about 4.2 gigajoules. Convert your answer to B into kilotons of TNT, that is, KTTNT. Compare your answer with the quick and dirty estimate of 10 KTTNT made by physicist Enrico Fermi shortly after witnessing the explosion from what was thought to be a safe distance. Reportedly, Fermi made his estimate by dropping some shredded bits of paper right before the remnants of the shock wave hit him and looked to see how far they were carried by it. 89. The purpose of this problem is to show the entire concept of dimensional consistency can be summarized by the old saying, you can't add apples and oranges. If you have studied power series expansions in a calculus course, you know the standard mathematical functions such as trigonometric functions, logarithms, and exponential functions can be expressed as infinite sums of the form summation from n equals 0 to infinity of a sub n x to the power of n equals a sub 0 plus a sub 1 x to the power of 1 plus a sub 2 x to the power of 2 plus a sub 3 x to the power of 3 plus dot dot dot, where the a sub n are dimensionless constants for all n equals 0, 1, 2, dot dot dot, and x is the argument of the function. If you have not studied power series in calculus yet, just trust us. Use this fact to explain why the requirement that all terms in an equation have the same dimensions is sufficient as a definition of dimensional consistency. That is, it actually implies the arguments of standard mathematical functions must be dimensionless, so it is not really necessary to make this latter condition a separate requirement of the definition of dimensional consistency as we have done in this section.